Okay, we're on. So
Okay.
welcome to New England Dynamics and Number Theory Seminar. And well, that's the first wartime meeting. It's a very sad period today, but still, I guess we can kind of divest from political events and horrible circumstances and look and do some mathematics. So Han, it's yours.
Okay, everybody. Happy Thursday. Welcome back to our seminar. And it's a great pleasure to have Irving Calderón from Durham University to speak in our seminar today. And the title of his talk is S-integral quadratic forms and homogeneous dynamics. Irving, the floor is yours.
Thank you very much. And thank you to the organizers for giving me the opportunity to speak here today. So today I want to present to you two results I got during my thesis. So these are two results about integral quadratic forms. This will be theorem AS and BS in this presentation. And both the statements of these, both these statements and the methods of proof are based on work by Han Li and Gregory Margulis. So I will present also the original results. This will be theorem A and theorem B. So the motivation for these original results, their theorems, and afterwards I'll talk about the extensions of those that I got in my thesis. So there will be three parts in this talk. In the first one, we'll discuss the main arithmetic problem that motivates the work. So we will discuss CS equivalence, of integral quadratic forms. And here, so we will present theorem A and theorem AS. And although you'll see that these seem to be purely arithmetical statements, in fact, the proof is based almost entirely on homogeneous dynamics. So in the second part, I will talk about the dynamics of CS equivalence. So I will sketch the proof of theorems A and AS. And finally, in the third part, I will present theorem B and BS, and these talk about small generators of S integral orthogonal. Okay, this third part will be very short. I think I'll just have time to present the statement. So the bulk of the talk will be part 1 and 2. So let me start. So this is the general setting. We will consider Q1 and Q2 to integral quadratic forms in the variables. That means that the QIs are polynomials, homogeneous polynomials of degree 2. And I ask the coefficients to be integers. Now we'll consider some ring R containing C, and we'll say that Q1 and Q2 are R equivalent, which I'll denote by Q1 tilde R Q2, if and only if there is a matrix gamma in JLDR that takes Q2 to Q1. So the classical setting is R equals C. So we're interested in studying the integral equivalence of integral quadratic forms. And more specifically, we're interested in the problem of C equivalence, which asks to find the method to decide if any given Q1 and Q2 are C equivalent. Okay, so we want a method that we can actually apply in practice. And the way in which we'll approach this problem, well, to say it in a naive way, the problem with this is that we have to search for an equivalence matrix in the infinite group GLDC. But actually there is a very nice result of Siegel that says that we can restrict the search of this equivalence matrix to a finite subset of GLDC. So this is Siegel's theorem. So he proves that for d greater or equal than 2, there is always an explicit function md with the following property. If we take any q1 and q2 integral quadratic forms in the variables, then they will be C equivalent if and only if we have a gamma 0 in GLDC that takes q2 to q1, but with the extra condition that the norm of the matrix is bounded by MD of Q1, Q2. So there are just finitely many matrices that verify this bound. So we can check the equivalence just by searching in this finite subset.
So MD is a map from the product of the set of quadratic forms?
Yes, yes. For a pair of integral quadratic forms, it gives me a real number.
Mm-hmm. Okay.
So an MD, as in theorem 1, we'll call them C search bound. Okay, so if we really want to use the result to answer the C equivalence problem, we need two things. First, we need to give explicitly the search bound. So find explicit MD. And since we don't want to check, since we don't want to look for the equivalence matrix in a really, really big subset, we would like to have an MD that grows as slowly as possible. So okay,
But what does it mean by the growth?
I will precise this in the next slide.
Okay.
So okay, so just let me say that the case of binary quadratic forms, it's there is a lot known in this case. It goes back to Gorkov-Gauss. So we will eliminate this case for now. We will focus in d greater or equal than 3 for the rest of the talk. So, well, and there is a conjecture that predicts that what's possibly this best possible growth for the MD. And well, in short, the conjecture says that we can have an MD that it's polynomial in Q1 and Q2. So here is the statement. This is a conjecture of David Masser. And it says that for any d greater or equal than 3, we can always find a search bound of the following form. We have some power of the product of the norm of the quadratic forms, norm of Q1 times norm of Q2 times some constant. And here, if Q is sum of Aij, Xij, then the norm is simply the max of the absolute values of the coefficients, and AD and BD are just positive constant that depend only on D. So depending only on the number of variables. Okay. So this conjecture of Masser, the first, well, lots of cases of it were established by Rainer Diekmann. So he establishes Masser's conjecture. First, for quadratic forms in 3 variables. And then for d greater or equal than 3, subject, well, provided Q1 and Q2, verify extra hypothesis. These are not too restrictive. For example, one of those is that the determinant of the quadratic forms is free of cubes. But anyway, there are some hypotheses that need to be added. And the proof relies mainly on analytic number theory. Okay, but the complete solution of Masser's conjecture is due to Lie and Margulis. So, and the solution is what I call here theorem A. It is in fact a simplified version of the result. Well, here it is. So they prove that if d is greater or equal than 3, then there is the polynomial search bound that Masser predicted, but they make explicit the exponent. We can just take 13 over 40 d cubed. And the multiplicative constant can also be deduced from their work. Okay. So this is theorem A. And now for theorem AS, I just wanted to consider the same kind of problem, but now with respect to a bigger ring than C. So now consider C1 over N equivalence of quadratic forms. Okay, but before I give the statement, I need a couple of definitions. Okay, so SF will be some finite set of prime numbers, P1 to PL. And when we will add the infinity, and I will denote this by S. So S during all the talk will be a set like this. And now the ring of S integers is defined as C1 over PS, where PS is simply the product of the prime numbers in SF. If there are no prime numbers, we define PS to be 1. So when S is equal to infinity, CS is simply the integers. Okay. And so now we want to decide, given any two quadratic forms, integral quadratic forms, Q1 and Q2, we want to tell if they are CS equivalent. Okay, so this time we're considering equivalence matrices that may have rational coefficients, say Aij over Bij. So what we'll do this time is bound both the numerator and the denominator of an equivalence matrix. So in order to do that, I will say that for any gamma, a matrix with coefficients in CS, the S norm of gamma is simply the maximum of the infinity norm and all the p-adic norms for the primes in S. Okay. So giving an upper bound on the S norm of gamma is the same thing as giving an upper bound on the denominators and numerators of the coefficients of gamma. So here is the result I obtained. It's very similar. So now Q1 and Q2 are any integral quadratic forms in at least 3 variables. And we consider any finite set S as before. Then Q1 and Q2 are CS equivalent. If and only if there is a gamma 0 in GLD CS, taking Q2 to Q1, but this time the S norm is bounded again by norm of Q1, norm of Q2 to certain power. And I show that 2D cubes suffices. But this time there is also a contribution. There is a power of PS. So PS to the 19d6. And just a small remark, this notation that I'm using here simply means that F, well, there is a constant that depends only on D, such that F is less or equal than AD times G. Okay, so now we have seen theorem A, theorem AS, and now we'll move on to the dynamics behind the proofs of these theorems. Okay, So this is part 2. And we'll start first with the dynamics of C equivalence. And so to keep things concrete, I will focus in a simple example. So consider two quadratic forms in 3 variables, Q1 and Q2. So since we want to decide if they are equivalent over C, so let's assume that at least they are equivalent over R. We can easily check that. It's just seeing if they have the same signature. So suppose they are equivalent over R. This means that over R, Q1 and Q2 are equivalent to some diagonal quadratic form with coefficients plus or minus 1. I will call this R. Okay, so now what I'm trying to do first is to say in other terms when Q1 and Q2 are C equivalent. So the R equivalence of the quadratic forms are controlled by the group G, GL3R. The C equivalence is controlled by gamma, GL3C. And we will also consider the real orthogonal group of R. I'll call it H. And I will pick two matrices, G1 and G2, and G that take R to Qi. So now it's easy to describe all the real matrices that take Q1 to Q2. These are simply of the form G2 minus 1, H G1. So we see that Q1 is C equivalent to Q2 if and only if G2 inverse H G1 meets gamma. And a nice way to detect this condition is by using the space X, G mod gamma. And then we have 2 points, YQ1, well, YQI, GI gamma. So in other words, this is equivalent to saying that there is an H in H that moves the point YQ1 to YQ2. So we consider the action of H in X, and we call big YQ1 the H orbit of YQ1. So the C equivalence of our quadratic forms is equivalent to the fact that YQ2 belongs to big YQ1. Okay, so here is a picture of the situation. So we will suppose that indeed that's the case. So when our quadratic forms are equivalent over C, then we have this big space X, we have our orbit Y, Q1, and 2 points here. And to complete this dynamical picture, or to justify that, in fact, the picture is as nice as it looks in here, let me say that YQ1 is closed in X, and the reason is that Q1 is integral. So now, if we have an H that moves Q1 to Q2 as in the picture, so then G2 inverse H G1 is in gamma. And it takes Q2 to Q1. Since we have already fixed G1 and G2, the norm of this gamma is roughly the norm of this H. Okay. So, well, this is the picture. So if we forget for a moment about the arithmetic motivation, we're left with this purely dynamical picture. So consider some closed orbit Y, closed H orbit in X, and we consider 2 points in there. And the dynamical problem just consists in bounding the size of an H0 that moves the first point to the second. So, okay. And just a small remark is that, well, this problem is not very interesting when H is compact because the norm of H is always bounded. So, interesting case. Is when H is non-compact. And this is simply saying that the QIs are isotropic over R. Okay. Well, so this is the dynamical picture for the C equivalence. And now I want to convince you that the picture is virtually the same for the CS equivalence for NES. So to do that, I'll just consider the next simplest example when S has a single prime P and infinity. And consider two quadratic forms, let's say these two here. So now these quadratic forms over R, they are equivalent, they are positive definite. So over R, they are equivalent to the quadratic form sum of squares. And for most P, they are isotropic over QP. So both of them are equivalent to x1 square minus x2 square plus bx3 square. So this time we want to bound the infinity norm and the p-adic norm of an equivalence matrix. So it's natural to work over R and over QP. But instead of doing that separately, we will work over the product ring, QS. Well, I'll call R infinity and RP these two quadratic forms. And then QS will be R times QP. So if we consider the pair R infinity RP, this is a quadratic form with coefficients in QS. And we can summarize these two equivalences simply by saying that R is QS equivalent to the QIs. Okay, so now the game is almost the same as before. We'll consider the QS equivalence is determined by the group G, GL3QS. So it's simply the product of GL3R and GL3QP. And we'll pick this time F and G matrices in bit G that take R to Q1, R to Q2. And for the CS equivalence, we have to consider GL3CS, but we will embed it diagonally in G. And finally, H will be the QS orthogonal group of R. So now again, sorry. So by the same reasoning as before, Q1 is CS equivalent to Q2, if and only if. So we introduce X is again G mod gamma, YQ1 is gamma, YQ2 is G gamma. We consider the action of H and X, and big YQ1 is just the H orbit of small YQ. So the CS equivalence is the same thing as saying that YQ2 belongs to big YQ1. So the picture is almost the same as before. The only difference is that in my example, my orbit YQ1 will be compact always, because the quadratic forms were positive definite. And now the two facts that complete this dynamical picture are as before. YQ1 is closed in X. And a second fact that was also true in the C equivalence is that any closed H orbit in X has finite volume. So this is with respect to the H invariant measure. Okay, so now if we have an H that moves the first point to the second, it has a real coordinate and a p-adic coordinate. So in that case, G minus 1, HF is a pair gamma gamma. Gamma is in GL3 CS. And it takes Q2 Q1. So comparing the real and the p-adic coordinates in this equality, we see that the infinity norm of gamma is roughly the norm of H infinity, and the p-adic norm is roughly the norm of HP. Okay, so again, if we forget about the arithmetics, we're just in this dynamical situation where Y is any closed H orbit, and we're given 2 points there. And this time we want to bound the size of an H moving the first point to the second. So as before, this problem would be very easy if H were compact, but in the concrete example we're looking at, H, so our quadratic forms, remember that they were positive definite, so H infinity is compact, but they were isotropic over QP, so this is not compact. And now I will give the main idea to answer this dynamical problem. And the argument will be using a mixing space. So the starting point of this is the next fact. Here we have another picture. Y is again a closed H orbit. We have 2 points there. So it turns out that there is a finite index of subgroup H naught of H. So H naught, finite index subgroup of H. It is also a product H infinity naught times HP naught. And it has the property that if we consider any closed H naught orbit, Y prime, then the p-adic factor, HP naught, the action on Y prime will be always mixing. So this tells us that for any L2 functions, phi1, phi2, Y, the integral of phi1 H inverse times phi2y will approach the integral of phi1 times the integral of phi2 over the volume of Y prime. So this just says that this term that I will denote E phi1, phi2 of H tends to 0 as H tends to infinity in HP naught. But even better than that, we can give a precise estimate of this error term. So for now, let's forget, well, here in the picture, we have the H orbit. It can break into a finite number of H naught orbits. Yeah, there are finitely many because H naught has finite index in H. But let's forget about this for a moment and assume that we are working with a single H naught orbit. So the bound for this error term comes from 2D results and holomorphic representations. So these are the Jacket-Langlands correspondence and the Lynch theorem. So if we combine them, they say that the unitary representation of HP naught on L2Y is tempered. So this says that the coefficients of this representation decay very rapidly, or in more dynamical language, we have a really fast mixing rate. So to keep things very concrete, let's consider these matrices, AM for M in C. So I wrote here the formula, it's very simple. And the fact that the representation is tempered means that the error term of phi1, phi2 at AM will be bounded by p to the minus m over 2 times the L2 norms of phi1 and phi2, provided that phi1 and phi2 are HP not smooth. So in this case, it's just being locally constant. These functions are invariant under some compact open subgroup of HP naught. So now that we have this estimate, the argument goes as follows. So here we have a picture just of our orbit Y. Mu will be an H invariant measure. And we will apply the estimate. So we consider two tiny neighborhoods, U1 and U2, around our 2 points. And we'll apply the bound of the error term to the indicator functions of UI. So the bound in this case says that the volume, so for any m greater or equal to 0, the volume of am u1 intersected with u2 minus volume of u1, volume of u2 divided by volume of y is bounded by p minus m over 2 times volume of 1, volume of 2 square root. So now that we have this estimate, we can choose m0 big enough such that the error term at am0 is strictly smaller than volume of u1, volume of u2 divided by volume of y. So if this whole term is strictly smaller than this term right here, this means that the first term has to be non-zero. So am0 u1 has to meet u2. Okay, so we have this picture. am0 sends a point really close to y1 to some point really close to y2. So now we can just correct this am0 slightly, and this shows that there is an h in h close to 0 that sends y1 to y2. Well, now if we write down explicitly this u1 and u2, and we can say exactly how big this m0 has to be. So doing all the computations, we obtain the next answer to the dynamical problem. This is proposition 3. So it says that if we take two matrices, F and G in G, and we'll suppose that there are 2 points in X are in the same H orbit, a closed H orbit Y, then there is an H in H moving Y1 to Y2, and we have this bound for the norm of HP. So there is some power of P, then we have a power of norm of F infinity, G infinity, so the real coordinates, also some power of FPP, and there is also a contribution coming from the volume of the orbit. So now that we have an answer to our dynamical problem, we go back to the original arithmetic setting. So remember that we had our two quadratic forms, Q1 and Q2, and F and G were matrices taking R to Q1 and R to Q2. Okay, so now the task is to replace the right-hand side of this inequality by something in terms of our quadratic forms. So it's easy to see that we can choose F such that the norm of F infinity is controlled by the norm of Q1 square root and the norm of Fp is less or equal to 1. And similarly for E and Q2. So this means that this term A here is controlled by norm of Q1, norm of Q2 to the 9. So now what about the volume term? Well, remember that in this case, Y was the orbit, the H orbit of associated to Q1. So this is H gamma. So to deal with this volume term of the orbit, we have the following proposition. If YQ is an H orbit in X associated to some quadratic form Q in 3 variables, integral quadratic form, then the volume of YQ is controlled by the square of the product of the infinity and p-adic absolute values of the determinant of the quadratic form. So this handles the, if we plug this into the previous proposition, we obtain our theorem AS. AS. Okay. And now, for the last part, I will just present very briefly theorems B and BS. So small generators of S-integral orthogonal groups. Now, the setting will be almost the same, but now we'll work with a single quadratic form, Q, integral quadratic form in the variables. And the motivation here is a classical result of Siegel that says that the integral orthogonal group of Q is always finitely generated. So Lee and Margulis obtain a quantitative refinement of this theorem of Siegel. So they show theorem B. Again, we restrict the attention to quadratic forms in at least 3 variables. So to generate the integral orthogonal group, we just need its elements xi, whose norm is less than norm of Q to the 3d4 times the determinant of Q to the d6. And what I wanted to do was just extend this to deal with all the S-integral orthogonal groups. So here is theorem BS. So again, if Q is an integral quadratic form in at least 3 variables, and now we take any S, any finite S, then the S-integral orthogonal group of Q is generated only by the xi, the elements xi, whose S norm is, now we have again a certain power of the norm of Q, and we have also a certain power of PS. Remember that this PS was the product of all the primes in S. So I think maybe I won't have enough time to sketch the proof, but let me just say at least the ingredient. So main two ingredients are quantitative results in reduction theory, forms, plus theorem A for theorem B and theorem AS. So, well, it might not be obvious why, but these two results are related. And I think maybe I'll stop here. Thank you. Thanks for your attention.
Okay, thank you very much. Thanks for your talk.
Thank you.
Are there any questions from the audience? Yeah, I actually have a question.
Yeah.
So at some point, you will still need to find the bound of the volume of your H orbit in terms of some data from the quadratic form.
Yes.
Right. And in doing that, did you use dynamical argument or did you find some new, like purely algebraic argument?
No, I follow the same argument that you use in the integral case. So it's the same dynamical argument works for
Okay.
CS equivalence.
Okay.
But yeah, we can also use the this the Y that we consider is essentially just OQQS mod OQCS. So there is also an explicit formula for the volume of these spaces. It's Prasat's formula. So I believe that will give also some bound if it's written like in very general language of algebraic groups. But if we unravel the definitions, we should get also something very simple in terms of the coefficients of the quadratic forms. But I didn't do it.
Okay. Okay. Thank you.
So, Irving, can I ask a general question? So,
Yeah.
so from your talk, it kind of I can see that you follow the argument of Lee and Margulis, and then you have the new space, and then you do something. So can you maybe summarize what? Sorry for the noise. What was the main new ingredient on top of? So what was the main new contribution? Which parts just extend more or less automatically or similarly, and in which parts you have to do something special? New.
Okay. So I would say that
what's the main new ingredient?
So basically, like the big ideas, I just follow the original argument. It's just a matter of seeing that all the technology that they used for the integral equivalence was also available in the S-adic setting. And it turns out it was, but it took me some time to do all the explicit volume computations and to work out all the details. So the main ideas are the same, and I was able to extend them just because like there is enough, this machinery is well developed to allow this more general result.
Okay, are there any other questions? Okay, otherwise, let's thank the speaker again. Thank you, Irving.
Thank you very much.
Yeah.